All right, there is a special case, and we should look at it. And that is when we have a fluid flowing and we've got a huge container. Maybe this is like the size of an above ground swimming pool or something like that, if you've ever seen one of those. And this above ground pool has a fluid in it. Usually it's called water. It's all in there. And that above ground pool is open to the atmosphere, so there's a, atmospheric pressure pushing down on it here. And it has a cross-sectional area. Those are little hashy marks to represent that this is an area. It's just looking worse and worse as I do that. But that's A1. And what happens when there's a little tiny hole in the side of that pool? Show me again. Oh yeah, it's going to squirt out and over. What's that called? Just this motion right here. Projectile motion. Oh my goodness. Yeah. And if this hole is really, really tiny, tell me about how do you see the water going down in the pool? Does it take some time for you to notice, oh, I think the level of the pool has gone down? Yeah, it usually does because it's moving so slow. So this little tiny area right here would be A2. Now, in terms of continuity, if A1 is huge and A2 is a little bitty hole in the side of the pool, then what's V1 versus V2? V1 is real little. And tell me about V2. It's huge. And by huge, it may be like 2 meters per second. So that means that small is really, really, really small if 2 is huge. Think about that. All right, then the other thing is, because this is a small situation where this height right here is not the height of a skyscraper or something like that, there is a pressure from the atmosphere pushing down on that fluid. And there's also a pressure from the atmosphere trying to hold that fluid from coming out. And because the height difference is so small, the pressure at the top of the pool is approximately equal to the pressure at the hole, because the height is, or delta y, if you want to call it delta y, is pretty small. For clarification, the delta y would be the distance between the top of the fluid in the pool and the hole. There's our delta y. So, let's apply this special case to Bernoulli's equation. Bernoulli's equation is pressure 1 plus 1/2 rho velocity 1 squared plus rho gy1 is equal to pressure 2 plus 1/2 rho velocity 2 squared plus rho gy2. Now if the P1 and P2 are both about atmospheric pressure, and they're both about equal because the density of air is really small and their height difference is really small, what can I do to this Bernoulli's equation? Yeah, I can take out the P1 and P2 because they're about the same. Now, if the area of the top of the pool is huge compared to the tiny little pinhole we put in the side, where the speed here, V1, is tiny, tiny, tiny. So V1, because it's very, very, very tiny, it's approximately 0. So let's make this approximately 0. That's because it takes a while for you to even see that the pool level is going down because it's so big. So then that leaves us with 1/2 rho. Oh, that was canceled out. So we're left with rho gy1 is equal to 1/2 rho v2 squared plus rho gy2. What can I do now? Anything? Does it matter what the density of the fluid is? Not if it is non-compressible. If it were compressible, the density of the fluid would matter because the density of the fluid at the bottom of the tank would be greater than the density of the fluid at the top of the tank. Right? So now we'll have GY1 is equal to 1/2 V2 squared plus GY2. So now let's solve for this velocity right here. Can I multiply by 2 on both sides? And then can I subtract GY2 from both sides? So would we be left with the velocity of the leak would be 2GY1 minus Y2? And that, B's and G's, is Torricelli's equation. But this is a special case. You have to have a case where the area at one point is much, much greater than the area at the other point. Therefore, the V1 is approximately 0. And P1 has to be approximately equal to P2 because delta Y is small. I ran out of space.